Today we are going to discuss electric field lines. We know charges. So when you have any charge, then it exerts force on any another charge. And this kind of force is not contact force. Means charge does not go to another charge for exertion of force. Rather, it creates all around its space some electrical nature, some electrical property with different magnitudes at different points. And this electrical property, you may say electric field in vector. In scalar it is called electric potential. So this electric field, which is the property of this electrical atmosphere which is surrounding this charge. So this electrical property, which can be explained as electric field, exerts force on any another charge when the charge is placed at that very point. So you have two charges. One is your source charge, which is creating some electrical atmosphere. With its strength in vector quantity is given by electric field. At any point, electric field has a unique value. At different points, you have different electric field. It is a vector quantity. And electric field or strength of this electrical atmosphere at any point is tested by any another charge that is called test charge. And the strength of electric field at this very point is given by charge is experiencing certain force, so that force divided by test charge. This is your electric field, force per unit charge. And this electric field is a vector quantity which has its magnitude, and also it is having some direction. You can find this electric field by doing calculations mathematically, by putting the values in formula. But the same electric field can be very simply estimated using the concept of electric field lines. And it is a very intuitive way, very good intuitive way to find electric field which is created due to any charge. So let us see all these things. What are electric field lines? When you place any test charge to test the electric field of any source charge, and if source charge is positive, so you will find that a positive test charge is repelled by this positive source charge, and this direction of repulsion gives the direction of electric field of this source charge. So you have so many test charges which are positive, and they will be repelled by a source charge which is also positive. And this radially outward direction from this source charge gives the direction of electric field due to this positive source charge. So electric field is radially outward due to a positive charge. Similarly, you can find the direction of electric field due to a negative source charge. You know that unlike charges attract each other. So all the positive test charge will be attracted towards this negative source charge. This is the direction in which the positive test charge will be attracted, and this gives the direction of electric field lines, electric field due to a negative charge. Electric field is radially inward due to a negative charge. So this is how field lines give you the direction of electric field in this way. What is the direction of electric field? It is radially inward towards a negative charge, and it is radially outward due to a positive charge. So here you find the direction, but with the help of electric field line you can also find the magnitude of electric field, the relative magnitude of electric field. So let us see how. Yes, one more thing, one more property of electric field lines. Two electric field lines can never cut each other. Here two electric field line I am drawing, they cannot cut each other. Why they cannot cut each other? This is not true. Why not true? Because suppose if you are placing a test charge over here, how can test charge be moving along the two directions? Test charge can move only along one direction. So this is not possible that at any one place the two field lines are cutting each other. Another way of saying the same thing is electric field is a vector quantity, and a vector has a unique direction. It cannot have two directions. And this is why field lines which are in the direction of electric field cannot cut each other. There can be only one electric field line at any one place. So next property of field line, initially we are just learning the property of these field lines. So the relative density of the field lines give the relative strength of electric field. Here you have field lines, and you know better that near any charge the electric field will be strong, and at a far point the electric field will be feeble. And how can you correlate this strong electric field with the field lines? Here you can see the density of field line is highest and electric field also is highest. So you can correlate the magnitude of electric field with that of the density of electric field lines. If the relative density of field line is more, then the strength of electric field, relative strength, will be more at that very place. Now for a single positive charge, these lines terminate at infinity. These lines continue up to infinity for a single point charge. But if you have a system of two charges, and if the charges are like charges, means they are either positive or they are either negative, then what happens? You can see now the field lines which were straight radially outward for a single charge, now they are not straight lines, they are curved lines. How can you find that these lines are curved lines now? So when you place any test charge near to a pair of these like charges, then you will find that the test charge is now moving on a curved path. And this curved path gives you the trajectory of electric field lines. If you are placing any test charge here, it will be moving along this curved path. You will find that these electric field lines are not straight. There is some pressure in between the two electric field lines. There is lateral pressure. And this lateral pressure suggests that they are repelling each other. There is repulsion. In between the like charges, you have repulsion. Similarly, if you take two unlike charges, one is positive and another is negative, then what happens? Then the shape of field line is changed. Now it is of this shape. What does this mean? This means that when you place any test charge at any one point, then it will move on this trajectory. It will move on this curved path and it will be moving from positive towards negative charge. When you will place another positive test charge over here, it will take this trajectory. It will not move along a straight path. It takes a curved path. And as we discussed that these electric field lines goes up to infinity for a single source charge. Now the scenario has changed. The length of this electric field line is reduced. There is contraction in the length. When it goes from positive to negative, its length is reduced. And this reduction shows attraction between the two charges. Here you can see that electric field lines start from positive charge and it goes up to negative charge. Direction is from positive to negative, and it is a terminated line. It is not a closed continuous path. It starts from positive and it terminates at negative charge. So now let us see some questions. Here question number 1. Which among the curves shown in the figures, you have several curves, cannot possibly represent electric field lines or electrostatic field lines? So here curve number 1. So everything is right here because the field lines are vertically upward from coming outside vertically with a positive charge sphere, and it is going in vertically in a negative charge sphere. But there is one drawback. Here you have closed continuous curve, and that is not possible in the case of electric charges, because electric field lines start from positive charge and it terminates at negative charge. As electric field is a conservative field, electric force is a conservative force, so on a round trip the net work done should be equal to 0. So it is not possible to draw a closed continuous curve for electric field lines. So your option 1 is wrong. Now option 2. You know that electric field line starts from positive charge and it go away from positive charge. So here electric field lines are going away, but on this curve you will find that it is going towards positive charge. That is not possible. Always field lines come out from the positive charge. It does not go towards the positive charge. So option 2 also is wrong. Now option 3. Here you can see that lines are coming out from positive charges. Up to here, option 3 is correct. Now here you have negative charge. And in negative charge, the field line should come in. But here it is going out. So option 3 also is wrong. Now option 4. In option 4, you have electric field directed not at all point perpendicular. Here it is making certain angle with the surface which is smaller than 90 degree. So when you take the component of electric field towards the surface, because here you can take component, then you know that force is equal to QE. There are charges in any metallic surface or any surface. Charge is not equal to 0. Here you find that Q is not equal to 0 and electric field along the surface is also not equal to 0. So the product of the two should not be equal to 0. So there is some force acting on any charge present on the surface when electric field is not making 90 degree with the surface. And due to this force, what happens? Due to this force, the charges will accelerate. Even though we have not connected any battery, the charge is moving. In which case? In a case when electric field is not perpendicular, it is making an angle smaller than 90 degree. In this case, without connecting any battery, you are obtaining motion of charge, that is current, and that is not possible. Without any source, charges cannot flow. So this option also is wrong. Now fifth option, you have two like charges and electric field lines coming outside due to positive charge. So it is true up to this point. Now here you can see there is lateral pressure also, because the field lines are not going straight way. They are pressurized away from each other. There is lateral pressure. So this option 5 is your correct option. 5 is correct option. Now let us do another question. Question number 2. Figure shows 3 different patterns of electric field lines. You have 3 different patterns of electric field lines. In each pattern, a proton is released from rest at point P. At point P, a proton is released and then accelerated towards Q. A proton is released from P and is accelerated towards Q. Rank the linear momentum and energy of the proton. In which case out of the 3, energy is highest, linear momentum is highest. So let us do. Here it is showing electric field. The field lines is showing you the magnitude and direction of electric field. Here the field lines are close to each other. Density of field lines is highest in this very case, in case C, and therefore you can easily assume that electric field at C is highest. Density of field lines is highest, electric field is highest. Second highest density of field line is in the case of this B. And here the field lines are least dense, so here electric field should also be smallest. Now let us find force. We know that force is equal to QA, and we have the same proton in all the three cases, no any another charge, the same proton is there. So charge is same, but what differs? Electric field differs in all the three cases. So force should differ. Force would be highest in the case of C, then there will be force of B, and force in case of B should be greater than force in case of A. So we obtained force, and this is why acceleration in C should be greater than acceleration in B, and it should be greater than acceleration in A. So change of velocity will be highest in the case when acceleration is highest. Here Vc must be greater than Vb, because acceleration while going from this point to this point, change of velocity will be highest one. So you can say Vc, you may write also, let me write, acceleration is change in velocity, Vc minus initial velocity was 0 by time, should be greater than Vb minus 0 by time, it should be greater than Va minus 0 by time. And this way you find that Vc is greater than Vb, it is greater than Va, and this says that since we know kinetic energy is equal to half mv square, kinetic energy depends on velocity. Mass is same, mass is the mass of proton. So the case in which velocity is highest, kinetic energy is highest, and therefore you can say kinetic energy of C is greater than kinetic energy of B, and it is greater than kinetic energy of A. Similarly, you can say momentum. What is momentum? Momentum P is equal to mv. Momentum also depends on velocity. Mass in the three cases is same, but velocity is not same. So a momentum will be highest, P will be highest in case of C, then in case of B, and then momentum in case of A. So this is how you will be doing the questions. Now next question, question number C. Question number 3. Figure shows track of 3 charged particles. You have 3 charged particles. Let me draw how the charged particles are moving. Here one charged particle, it is going along this direction. You have another charged particle going along this direction. And then you have a charged particle going along negative plate. So these are the charged particles in a uniform electric field. Electric field is uniform. Give the sign of the 3 charges. Which particle has the highest charge to mass ratio? So you have 2 questions. Firstly, you have to give the sign of the 3 charges. Now the charges which are attracted towards positive plate, we know that like charges repel each other and unlike charges attract each other. So positive plates would be attracting only negative charges. So charge 1 and 2 are negative. Similarly, unlike charges attract each other and negative plate is attracting unlike charge, that is positive charge, and therefore charge 3 is positive. So this is answer of this first question, sign of three charges. Now second question, which particle has highest charge to mass ratio? We have to find charge to mass ratio. Now let us start in this way. Since we know that force is equal to QE, it implies that MA, force is equal to mass into acceleration, MA is equal to QA, and it implies that acceleration is equal to QE upon M. So from here we obtained acceleration. Now as there is a force acting not in horizontal direction, in horizontal direction there is no force. The charge will be moving uniformly. But when it enters, the charge enters in the region of this electric field, then the charge is acted upon by electric field, which is directed along downward direction. Here you have electric field in this direction. So when charge come in this region, then the negative charge will be moving opposite to this electric field along this direction, and positive charge would be moving along electric field. A force would be acting, and an acceleration will be there in vertically downward or vertically upward direction. So there will be certain displacement in this direction also. Now we can apply Newton's equations of motion, because when acceleration is there uniform, you can apply Newton's equations of motion. So on applying Newton's second equation of motion, that is S is equal to ut plus half at square. Now look here. Though the charged particle is in velocity, but the velocity is along horizontal direction, and here force is acting in vertical direction. So in vertical direction, the initial velocity was 0. Now when it comes in this region of electric field, now there is some movement due to this electric field, but the initial velocity along vertical direction was 0. So using all these things, S is equal to 0 plus half A is your QE by M, and T square. So from here you can see that rest of the quantities you may consider as constant, electric field as constant, and then you can relate distance traveled in vertical direction to that of charge by mass ratio by this one, because rest of the quantities can be considered as constant. So S should be directly proportional to charge by mass ratio. So if distance traveled is large, then charge by mass ratio of the particle is also large. Here you can see what is vertical distance in case of 3, this much. In case of second particle, vertical distance is this much. And in case of third particle, that is particle 1, it is smallest vertical distance. So from here you can see largest vertical distance is for particle 3, second largest for 2, and third largest minimum vertical distance is for particle 1. And therefore, since vertical distance is proportional to charge by mass ratio, you can say that charge by mass ratio for particle 3 is greater and greatest and is greater than charge to mass ratio of particle 2, and it is greater than charge to mass ratio of particle 1. So this is how you can do all these questions. Now I conclude.